Hello everyone. In this video, this is the problem that we will solve. On a road curve, y is equal to x squared. A car passes it with a speed increasing at 2 meters per second squared. Determine the velocity in meters per second at point x1 meter, where the acceleration of the car is 2.8 meters per second squared. Okay, so solution. Now, in this problem, this is under the curvilinear motion because if you notice, we have a road curve. Now, which among the components should we use? We should take note of this word, speed. Once this word comes out in the problem, it is a big hint that you need to use normal and tangential components of the curvilinear motion. So, let's first identify what we need and what are the given values. So we need to determine the velocity. Okay? We need to determine the velocity at point when the point is x is equal to 1 meter and when the acceleration is 2.8 meters per second squared. Now we have also other givens such as the equation of the curve as well as the speed increase or the amount of increase in speed, which is the 2 meters per second squared. Now the question is, what is this value? This is actually acceleration, but due to the word that it is the acceleration of the speed, it is your tangential acceleration. So we now have these three given to solve the velocity. Now in our module, we do have in the normal tangential portion, we have the formula for velocity as the normal acceleration is equal to the v squared over the rho, where rho is now the radius of curvature. So to solve the v, we need the normal acceleration and the radius of curvature. We can solve the radius of curvature by the formula in our module, which was 1 plus dy over dx squared, quantity 3 over half over the the second derivative of the path. Now we have the first derivative of our path, which is y is equal to x squared. The first derivative, this becomes dy over dx is equal to 2x. And we have the second derivative becomes 2. So solving for the radius of curvature, this is 1 plus 2x, where x is equal to 1, so 2 times 1, so that is still 2, squared quantity 3 halves. Then we have the absolute value of the second derivative, which is 2. So we'll have the radius of curvature. This is now 1 plus 2 squared quantity 3 halves all over the absolute value of the second derivative, which is 2 or positive 2. So our radius of curvature is 5.590 or 5.59. This is in meters. 5.59. So we have the radius of curvature. We need the normal acceleration to solve the velocity. To solve the normal acceleration, we can make use of the tangential and the actual acceleration. And they're using the relationship which we have, the a squared is equal to the squared of the normal acceleration plus the squared of the tangential acceleration. We have 2.8 squared is equal to the normal acceleration squared plus 2 squared. Solving this, we'll have an is equal to square root of 2.8 squared minus 2 squared minus 2 squared, square root of 2.8 squared minus 2 squared. So we'll get 1.96. 1.96. This is now in meters per second squared. So this is the normal. Okay, normal acceleration. Okay, square root of 2.8 squared minus 2 squared. Okay, rearranging that. So we now have the normal acceleration. We have the radius of curvature. We can plug it here. This is 1.96 v squared all over the rho, which is 5.59. Solve for v. So finally we have v would be square root of 1.96 times 5.59. Okay, so this is cross multiplied, then square root both sides. So 1.96 times 5.59, then square root. We have 3.31 meters per second. So we now have the velocity of the car at 0.1 meter, where at point x is equal to 1 meter, where it has an acceleration of 2.8 meters per second squared. So this is now the answer of the problem.